ask the speaker is Farwa Bawar. Thank you.
Hello, so this is John Clark, a Farwa Kuhn on distributed approximations and independence. So, you're given a node-weighted graph, and the goal is to find an independent set.
Please use mine.
And the goal is to find an independent set, a set of non-adjacent nodes with maximum total weight, like the blue nodes here. Now, solving this problem often in general is considered to be hard, and it's actually the case in the distributed setting. Even getting good approximations is believed to be hard, unlike some special graph families. So we focus on efficiently approximating weighted independent sets on sparse graphs in the congest model, which I assume most of the audience is familiar with, and I have no idea what's going on. Okay. So I will not elaborate further. I hope you are familiar with the congest and the local model. But I want you to remember that at the end of our distributed algorithms, every node needs to know it's part of the solution, so whether it's in the independent set or not. Okay. So remember, we're working with sparse graphs, where sparsity is measured with our velocity, which is the minimum number of disjoint forests covering all of the edges. So our first results improve on the most recent time approximation trade-off of the problem, the weighted problem, as a function of our velocity. So earlier work achieved an almost 8 alpha approximation in roughly log squared delta log n time. That is the maximum degree. We improve on this approximation by a factor 2 in roughly log squared alpha plus log star n time. So if you think of epsilon being fixed, our result is polylog in alpha, the result is polylog in delta and n with a larger constant power. So later, this approximation was improved by Gill. Okay, sorry. This is an old laptop, so that's why this was happening. So this approximation was improved by factor, to get a factor 2 plus epsilon alpha in alpha log n over epsilon runtime. Now, okay, great. This is a brief announcement. All right, so just do that, huh? Right, my notes also are there. So,
just leave it like it is, that's fine.
That's fine? Sorry. So, what we do, I already mentioned that. Okay. So, if you think of epsilon being in this range, our results yield a larger independent set. Now, it's not directly to see, but if we apply our algorithm for a redefined epsilon, say epsilon over 4, and compare the bounds, then you can see it then. And we achieve this in exponentially faster in alpha runtime. So think of epsilon being this 1 over square root alpha. Our result here, you get alpha, if you look down, and then above log to the power 4 alpha, faster than this result where you have alpha, and think of square root alpha, the 1 over epsilon. Okay? Now we can talk about the simplest sparse graphs trees with our velocity 1. And the best known result previously was a half approximation on rooted trees in tight log star n rounds. And our result, we get 1 minus epsilon approximation on general unrooted trees in log star n over epsilon round types. So we proved the lower bound, and hopefully in the time I have left, I'll talk about the upper bound, because it's simple and cute, and the other results are just technically more challenging. Okay, so now we have a node-weighted tree, and the goal is to find a 1 minus epsilon approximation. So, our result is based on a previous clustering technique, low diameter clustering technique, that was originally developed on planar graphs in the local model. So we adapted for trees in the congest model, and to see how to do so, let's just understand how this local planar algorithm works. Chikrinov et al. Start by assigning edge weights, which is the minimum of the endpoint weights. Okay, so now we have an edge weighted tree. And then they find the D-epsilon clustering, which is a partition of the nodes into smaller connected subcomponents, subtrees in our case. Each cluster of diameter at most D, and the intercluster edge weights is at most epsilon fraction of the total edge weights. So assume you have such a clustering computed. To get an independent set now, you just brute force the solution locally in every cluster. This you can do in the local and diameter time. What we do in Congest is a dynamic programming implementation, which can still be done in cluster diameter time. Combine all the results, that's your independent set. Not really, because you can have conflicts in between. Two nodes on an edge might join. So what they do is remove the minimum endpoint weight, and this is the independent set that you get. This is how much you remove due to the second property. Now, by simple observation, and because we're in trees, you get a 1 - 2 epsilon approximation, and it's enough to what we want. But the question is, how efficient can we do this in Congest? So, the first step is easy. The last step I said, dynamic programming gives us a cluster diameter time. It's the second step that takes d log star n rounds in the planar local approach. So if we apply it on trees, there's no congestion, it still runs at the same time. And what they show is actually a cluster diameter of poly 1 over epsilon. So that's really the runtime, which is not tight. So what we want is a 1 over epsilon cluster diameter to get this tight bound. And that's what we're going to try and do, shrink this cluster diameter to 1 over epsilon. So to do so, let's just understand what's the problem with their clustering approach, what's holding us back from doing so. So what they really do in that step is iteratively grow clusters, where in each cluster growing step, see, this I can't, an old thing. Okay, in each step, the cluster diameter grows by a factor 9, whereas the intercluster edge weights shrink by a factor 3/4. So, fast, okay, you can do that. And that's the problem. The cluster diameter is growing faster than the boundary edge weights shrinking. And because of this, we get a poly 1 over epsilon cluster diameter, rather than 1 over epsilon, which is what we want. And that's what we're going to try and do by balancing these rates. In the following, and quickly, I'll give you the intuition. So say you have a d epsilon clustering, and what we're going to do is allow ourselves to run a few iteration steps of this planar clustering approach until, say, everything outside is 1 over 4, okay? The weights outside is 1 over 4. And the intuition here is once the cluster grows too quickly, we're going to try and shrink it back using our tree structure property and rebalance the rates. So what we do essentially is as follows, and quickly. Each cluster, we root it, and we layer the edges at distance modulo 4 over epsilon from the root, all right? And then we choose the layer with the minimum total edge weight, say it's E2 here, and then we're gonna remove them. So now we split the clusters into clusters of smaller diameter, each of at most 4 over epsilon. And what happens outside is that we double the intercluster edge weights, but that's no problem. Here we have an epsilon over 4, so really everything outside is half now, and that's the cluster diameter, which you can still see it like this, so everything's really rebalanced in this intermediate clustering step. I'm almost done, and we can do this quickly. And yeah, that's what we want. If we start with an initial trivial 1-1 clustering, where every node is just a cluster on its own, right, and we repeat this whole scheme logarithmic 1 over epsilon times, then you really get the desired clustering we want, an optimal time, and thus get this close to an optimal deterministic on trees, an optimal time I can just. Thank you.